The first example that we want to develop in TLA Plus is the one you already studied in EECS 3342. If you can recall the bridge controller example. But don't worry, we may not actually want to cover every single detail of the bridge controller and its refinements from scratch. Instead, I will try to mention just enough details in this tutorial video so that you can develop together with me the initial model for the bridge controller. And the exercises will be the subsequent refinements for the bridge controller, in which case I'll try to give you some quick resources so you can just brush up the details. Of course, if you really want to be more efficient in recalling the details, you can feel free to speak to me, maybe in the office hour if you need to, or during the scheduled lab. We'll see how that goes. Alright, so we're going to go back to this TLA Plus Toolbox IDE maybe in the next part of the tutorial. For now, let's do a little bit of paperwork just to clarify the conceptual understanding of the bridge controller. Let's do that. Alright, so there are two things I want to talk about. One would be the overall requirements documents for the bridge controller. What is it intended to build? Apparently, a bridge controller. Let's recall the details. So we got three notions over here. We got the so-called mainland over here, and also we got the island, and we want to connect the two sides by a single bridge, and the bridge is supposed to be one way, and also there might be some traffic lights to regulate the traffic. And of course, we actually covered the notion about requirements documents. So this notion here will still be applicable in the current course 4315 because you're still trying to build a system from informal requirements. So that requirement there should be available in the first place. Let's take a look at the requirements document very quickly. So remember the E description versus the R description, right? Let's recall very briefly. You will still need these concepts in the current course. So the so-called E description over here, oh, you know what, let me use a different color just for easier for you to see. The E description over here, all the environmental constraints. So these are the E descriptions. So they actually documents the working environments constraints. Of course, they are beyond your control, in which case you don't really have to make them work. They actually assume to be the case. And how do you usually encode the E description? Typically, you will try to declare them as axioms or certain assumptions of some sort. Let's take a look at the assumptions we can make about a bridge controller. So the system is number one. The system is equipped with two traffic lights with two colors, green and red. And if you recall what we did in 3342, we don't really actually introduce the notion about green and red traffic lights until maybe the second refinement or the third one. But in the initial model, we don't really talk about this traffic lights. So the idea about correct by construction, which we also recall in the lecture, we don't really have to encode every necessary detail in a single initial model, or even in a single model in the intermediate level. We don't have to. We gradually introduce all the details, accumulate all the details as we go. Let me also remind you very quickly about this idea. Correct by construction. Correct by constructions. And don't forget, in the current course 4315, one of the very important learning outcomes is not to really forget about the details and principles you learn in 3342. You have to always try to compare yourself. What's really the difference between the two approaches we are taking between the two courses? So correct by construction is what we learned in 3342, and the essence of it is, number one, do not encode all the details in a single model. And what should we do instead? Instead, we want to gradually introduce more details in the refinements. Instead, distribute the details in the gradual refinements. Distributes details, in which case there'll be the variables. All the necessary variables, for example, variables for the counts of the number of cars in the island, the count of the number of cars in the bridge, traffic lights, and many other things. So you don't really have to encode them in a single model initially. You don't have to. Distribute variables and properties in the gradual refinements. Models. And of course, these refinement models will be multiple ones. So that's why it's plural. All right, it's a very quick recap about what we learned about corrects by construction. And let's go over the rest of the E description here. So we got traffic light. It should really control the entrance on both ends of the island. There should be the entrance for into the island, and also maybe entrance to the mainland and exit symmetrically as well. Okay, the third one. Cars are not supposed to pass on the red traffic lights, only on the green one. So this is also something we have to be sure that is documented in the requirements documents. So in our formal model, there is no notion about what if a driver actually simply passed through the red lights, or they simply stop on the green lights. So we don't really have any notion about such abnormal driver who behave very weirdly. Our model is not sophisticated enough to catch such weird behavior driver. So that's always remember, whenever you want to build your formal model, you're not claiming that it will just work under any circumstances. There's certain limited working environments which you have to assume, right? In this case, all the drivers will be legal driver. That's something we assume. And the system is equipped with 4 sensors with 2 states on and off, and we don't really have sensors until later refinements. And this part here is just about the purpose of the sensor, and that'll be only for the later refinements. And if I can recall, in 3342, in winter 22, we didn't really get to the last refinement with the sensors and actuators. So for this lab over here, and also for the exercise, you don't really need to worry about this particular refinement. If you're interested, explore it by yourself. Okay, it's really optional. And the second kind of descriptions in the requirements document will be the so-called R description. Let's take a look, and then we'll make a notes, and then we can move on to the specific details about the initial refinements. The initial model for the bridge controller, which we want to code up in TLA plus, right? So you can kind of build a connection between the 3342 approach for theorem proving and also 4315 approach for model checking. All right, the second kind of description over here, which I'm going to highlight in orange, R description, right? Let me write it down maybe over here. R description. So R description over here. So they actually documents the simplest term, intended functionalities of the system. The intended functionalities. And of course, these functionalities will be up to the task of the developer. You have to make sure the abstract state machine or the final code should really reflect these intended functionality. And again, the idea will be you want to do correct by construction. You don't really want to put all the details in a single model. Right? You want to gradually introduce all the intended functionalities into the model, so they'll be accumulated over time. Right? Let's take a look at the functionality that's intended. So the system is controlling cars on a bridge connecting the mainland to an island, right? So that means somehow you want to keep track of how many cars are on the bridge and also how many cars are on the island. There should be some number that should be recorded on the bridge, and there should be some number recorded on the island, right? And requirements number 2, the number of cars on the bridge and the island should be limited, right? So what it is talking about is the total number of cars on the island and on the bridge. If that's certain number, let's say n, or small n for variable. If these numbers have the sum variable n, you should really make sure that should be less than or equal to certain limits. And that's something we have to encode in the model. And that's exactly what we will do in the initial model. We'll get there. All right, finally, the bridge is one way or the other, not both at the same time. So you should always make sure if there is already at least a car going this way or on the bridge. In that case, the flow going the other way should be exactly 0, right? If you recall what we did back in 3342, we spent quite a bit of time of talking about how we can express such property as invariant property and also how we can prove them. It's not exactly covered in this course over here, but we'll try to model check them rather than theorem proving them. That's something we'll see. All right, so that's about the first part of the review. I just want to remind you about the idea about requirements documents and also the notions about E description and also R description and also correct by construction. So please make sure these are not really forgotten from your previous course. They're good stuff. And the second part of the review is going to be about how we can build the initial model. And as we said before, correct by construction principle, you don't really try to encode every single detail in the initial model. You try to make it as simple as possible. So I'm going to give you a direct summary about what the initial model should look like. And this will be the basis for us to build the TLA plus module or specification in the next video. And for the initial model is only going to address requirements number 2, which is about the number of cars on the bridge and on the island will be limited. So there should be some number over here, and there should be some number. Oh, sorry, let me say it again. So we got the mainland over here, and also we got the island and the bridge. And if you recall the general diagram over here, so initial abstraction over here is to collapse the island and also the bridge into a single complex over here. This will be the first one, and the second one will be the mainland. That's kind of the abstraction we're doing. And another analogy that we made back in 3342. Imagine that you're trying to look down the island bridge mainland construction from maybe 1,000 miles above the sky, right? Very high on the sky. In which case, you cannot really see maybe even a bridge because bridge is very small. So all you can see will be just like this. Just the island and bridge compound and also the mainland, right? That's an analogy. If you're interested, you can definitely maybe look at a pre-recorded lecture from last year just to recall, but it's optional. All right, so in the initial model, we simply don't have the notion about bridge. That's something I would like to just address. Okay, in the initial abstraction, it's really important to note there is no notion of bridge. It has been abstracted away. Okay, that's the beauty about refinements, because you can only introduce certain details when necessary later in the subsequent refinements. All right, let's go over the model quickly, and then I want to remind you very quickly about how we can build the state transition diagram. But one thing you can take a note as a look ahead. In TLA Plus Toolbox, once you have built your specification, you will be able to generate some state diagram as well. By the way, for Rodin, it also has the capability to generate a state diagram, but we didn't really cover that part in 3342. Anyway, you don't need to worry about Rodin anymore. For TLA Plus, just remember, once you somehow translate this diagram into the valid TLA Plus syntax, you will be able to generate state diagram automatically. And that will be the very valuable source for you to actually debug whenever you got any violation of the property. That's something we'll cover in the later video. All right, so we have some constant d, and we have some variable n. You can think about the d over here being a natural number, right? You can see axiom. Axioms are those properties which we don't really have to prove. We just assume them and take them for granted, right? So we're saying that d is actually a natural number. And if you recall, the definition of a natural number, right, for our purpose, is going to be starting from 0 until all the way to plus infinity, right, including 0. And then d here is denoting the maximum number of cars in either the island or the bridge, i.e. is in this particular island and bridge compound over here. There should be a maximum constant d in the island bridge compound. Right, and the axiom here talks about d should be can be 0. Of course, may not be very useful. That means no cars can ever be in this particular system, but that's the base case. And then we got larger and larger d until maximum, right? And we got variables over here. N would be the number of cards that's currently in the island or in the bridge, namely in this particular compound, right? That's the n. And also n should be a natural number. You can think about initially n will just be 0, in which case the system is just starting, or simply all the cards have gone, from the island and the bridge, maybe overnight, right? Once the island has been closed for entrance. And then n should be less than or equal to d. So that's a very important invariant property, right? And if you remember, that's our naming convention over here. The 0 over here is about model 0, initial model. And 1, 2, and over here are just numeration of all the invariant property. And if you see INV over here, so these are the safety invariant property that should be true for every possible states of your system. So that's the safety invariance that must be true, must be preserved, or must be held in every states. All right. And for the initial model, there are only 2 events, namely either a car will actually go out of the mainland and go into the complex. You can think about either go into the bridge or go into the island, either way, but it will be considered the same by just ML out. Or a car going out of either the bridge or going out of the island, they will be considered as ML in. Oh, sorry, let me say it again. So this one is actually more restrictive. So when we say a car going out of this particular compound into the mainland, it will be covered by MLN. So the only possibility will be going out from the bridge into the mainland. Let me say it again. MLN, in this case, you can think about MLN over here is going to be going from the mainland onto the bridge over here. That's one. And also ML out is going out of the bridge onto the mainland over here into the compound. But for the initial model, we don't really distinguish between island and the bridge, right? That's all you need to know for now. All right, and the ML out for now, we just say the counter should be incremented, and here the counter should be decremented. And you may just want to pause the video just for 30 seconds and think about, are these two events properly specified? And if you try to recall, what would be the ingredients for a single event? So this part over here, let me remind you, that's called the action. Okay, that's called the action for your updates. And isn't there another components or ingredients for the events called the guards? At the moment, if you don't really have any guards for the events, which means the event is always enabled at the moment, ML out and ML in. So both events currently are always enabled because the implicit missing guard simply denotes true. Implicitly, the guard is simply just true, right? So that means both events are enabled. Are these specification of the two events correct as far as preserving or establishing the invariant properties over here are concerned? So that's a very important question for you, right? You can think about it. That's something we addressed back in 3342. We wouldn't really cover that again from scratch, but instead we're going to show to you how you can reveal what the problem might be, if any, in the TLA Plus tool using a model checker. That's something we'll do. But for now, I just want to show to you very quickly, how can you link a formal model like this in some textual syntax over here into another formal model like a abstract state machine, right? Like a state transition diagram. Let's make the following assumption. Let's say we have D being 2. So that means we can get maximum 2 cards on the island and the bridge in total. It can be 0, can be 1, can be 2, but it cannot be 3, of course. And let's assume that n will be initialized to be 0, which is very reasonable. Initially, there's simply no card in the compound of the island and the bridge. And how do we really visualize the system over here as a state transition diagram? right? That's something we want to review very quickly. So what we'll do is, I already got some notes over here. I can copy. The initial state for the system will just be the constant d will never be changed, but the variable n will just be initialized to be 0, which we assume. And we use the arrow over here, a one directional arrow over here as initial states. You can think about some init events is actually should occur in order for us to establish all the invariants. And from this state over here, we should think about depending on this depending on the variable value for this state here, it may enable or disable each event in the system. In that case, of course, you have to determine from this states all the enable events may actually occur, in which case it's going to branch to its own subsequent states. So what do I mean? Let's say for this state specifically, n is equal to 0, is it going to enable ML out? The answer is yes, because its guard in this case is trivially true, because it is implicit, it's missing. And the same states, is it also going to enable the guard for this second event MLN? The answer is also yes, for the same reason, because the implicit guard here is also true, right? Because it's missing. And that means from here, from the first states, we can either take ML out over here, and we can also take ML in over here, right? Let's now see what the corresponding state will look like. And then from there, we are actually going to give you some remark, and then we can move on to the next part of the tutorial. So this one here, and also this one here. Very easy for you to actually fill in, right? Let me just make this a little bit smaller so it looks a little bit better. Okay, one here, and also one here. Right, so you can see over here, if n is equal to 0, and then we take, let me take a different color. If n is equal to 0, and then we take ML out, the action part is n should be incremented. So n should be incremented from 0 to 1. And then ML in over here, ML in is going to decrement the n by 1. So from 0 to minus 1. You can already see we got one example trace over here that's going to lead to some invalid states, which will violate the invariance. You can see minus 1 over here will violate this invariant here. It's not a natural number anymore, right? Let's make a note. So this one here violating invariance 0, 1, because minus 1 is not really a natural number. All right, hopefully you're following, right? It's really the good stuff that we learned from 3342. It's been a year, but it will be now the time to brush up. Okay, and of course, this will be some illegal states. And what about this state here? This state here is actually fine. So what were we talking about here? We're talking about from this initial states, it may either take ML out or you may take ML in. But in the case where ML in is taken, you might just lead to some invalid states, which is not good. If there's any possibility that it might lead to some invalid states, that means your system is not 100% safe. One more thing to say. How do we come up with the entire state diagram conceptually? And for this subsequent states, you also want to think about what events does it enable. Since we only got 2 candidates over here, and both of their guards are simply true, so you can also take ML out over here. Let me just write here. You can also take ML out. You can also take ML in as well. And of course, if you want to do a little exercise on your paper, you can figure out what should be the state for this one here and what should be the state for this one here. You can also potentially see from this branch over here, if I take ML out and ML out, here n will just be equal to 1 plus 1 will be 2. If I just take another ML out, let's say, that's going to give you n is equal to 3. In that case, we are violating the second invariance, right? So there are 2 possible ways for you to violate the invariant property, either this way by taking too many ML in, or this way by taking too many ML outs, right? That's really something simple that you should be able to visualize yourself. All right, and all these can be revealed somehow by the model checker as long as you encode your encode your model and properties accurately, and also use the tool properly. That's something what we will show to you in the next video. All right, it's kind of a short, not too short, but it takes some time, but it's kind of like a brief review about what you should really know from 3342 for this particular tutorial video. I'm gonna include some resources for you in case you want to explore more about the details for the bridge controller. All right, in the next video, we're gonna see how we can encode this M0 over here that's not exactly correct, especially the guards. We're gonna see how we can do that in the TLA Plus toolbox.